Welcome to Maths with EJD. In this video, we're still talking about inverse Laplace, and the focus now turns to residue theorem. Generally, we know methods for inverse Laplace, like we've been seeing, actually includes partial fraction decomposition. So we decompose a rational function into partial fractions. So partial fraction decomposition. So we can then do the inverse from there. Then we have the convolution theorem, where you're looking for the Laplace inverse of the product of two functions. And then we have the residue theorem, which we are considering now, residue theorem. Okay. Now, having said that, we've seen partial fraction decomposition, we've seen convolution theorem. Now it's time for residue theorem. So residue theorem basically is a concept from complex analysis, complex numbers. So residue theorem, the residue theorem is a technique from complex analysis useful when dealing with integrals of rational functions. It can also be applied. It can also be applied to compute inverse Laplace transforms. Especially when the function has poles. When the function has poles. Poles are also known as singularities, or better still, points of discontinuity. That's points where a function is not defined. Okay. So if we have a function, a frequency domain function f of s with simple poles, we can compute its inverse Laplace, transform by evaluating the residues at these poles and applying the residue theorem. Okay, the inverse Laplace transform is given by f of t equals 1 over 2 pi I integral along a curve or so of f of s e raised to power st ds. So that's how we get the inverse Laplace using residue theorem. Okay, let's move on to an example. Okay, Example. So the same problem we've been solving all along, right? Given f of s equals 1 over s plus 1 into s plus 2. Compute the inverse Laplace transform using the residue theorem. Okay, now solution. So the first thing is to identify the poles. Identify the poles. So of course we have f of s equals 1 over s plus 1, s plus 2. So the function has poles at s plus 1 into s plus 2 equals 0. So wherever this is 0, then the function will have poles or points of, or singularities or points of discontinuity. That means that s plus 1 is either 0 or s plus 2 is 0, right? So that means s is equal to minus 1 or s is equal to minus 2. So these are the poles, right? So the next thing to do is to compute the residues at each pole. Compute the residues at each pole. So that means that at s equals minus 1, that's the first one, the residue of 1 over s plus 1, s plus 2 at s equals minus 1 is equal to 1 all over, of course, you exclude the first one that gave us the value, and you have minus 1 plus 2. Okay, minus 1 plus 2. That means that that is equal to 1 over 1, and that is simply 1. Okay, or I can do that straight. So this is 1 over 1, and that is 1. So the residue there is 1. Then we go for the other one. So at s equals minus 2, so the residue of 1 all over s plus 1 into s plus 2 at s equals minus 2. So we skip the one that will make it 0, right? And go for the second one. So we have 1 all over minus 2 plus 1. Okay. And that is 1 all over minus 1. So that ends up being minus 1. So if you look at it properly, right? Here, because this s equals minus 1 came from that. So we pick s. We pick s plus 2. And because s equals minus 2 came for s plus 2, came from s plus 2, so we pick s plus 1, and then that's how we get the residues. So now that we have the residues, the next thing we want to do is to sum the residues. That's the third step. Sum the residues. Okay, the inverse Laplace transform, is the sum of the residues, so that we now have now here if we sum the residues, that's gonna give us 0. Okay. Okay. Let me get this clear. Residue residues. Okay, the inverse Laplace transform is the sum of the residues. Simple poles, residue s equals -1. Okay. Okay, so um the contribution from this residue is to f of t. Okay, I think it's basically about the poles actually. F of s by s plus 2. Okay. Okay, so if we have a simple pole at s equals a, the residue is that, then each simple pole at s minus a contributes a term. Okay, good. So the residues in this case, well, I think they are just for information. So the poles are the things that actually give us that actually give us the actual thing, right? So since we have calculated the residues now, the inverse Laplace transform is the sum of the it's not necessarily the residues now, okay? It's the sum of the contributions of residues, okay? And this the first one, because this is s minus 1, so this is going to contribute f of t equals e raised to power minus t. Okay, and because this is s minus 2, this is going to contribute f of t. Let's say this is f2 of t, right? That is e raised to power minus 2t. That's what this is going to contribute. Just like this one would be f1 of t. Okay, so the inverse Laplace transform is the sum of the contributions of the residues, okay, given as given as uh given as f of t equals f1 of t plus f2 of t, and that is simply e raised to power minus t plus e raised to power minus 2t. So it's about the poles, right? And that is what the answer is in that case. Okay, and it's necessary that t is greater than 0. That's a necessary condition. So using the residue theorem, that is what we get. So if we want to talk about a key takeaway here, we can do this. Key takeaways. Okay, key takeaways would be that you know, we have for residue calculation, right? So we have that for a simple pole, at s equals a, the residue is the residue of f of s at s equals a, okay, and the limit as s approaches a of s minus a multiplied by f of s. So this s minus a will automatically cancel the other s minus a, and that's how you see that here it's more like we are saying s plus 1 multiplied by this whole thing. So s plus 1 will cancel s plus 1. So I mean s plus 2 rather, because this one is coming from s plus 2. So s plus 2 will cancel that. So that's why we have this left. So this is the summary now. So wherever the particular pole is coming from will be multiplied, will be cancelled out based on this condition now. So for a simple pole at s equals a, okay, the residue is what we've said, this expression now, okay, and then we can also have another point, which is that each pole, each each simple pole each simple pole at s equals minus a contributes a term of the form e raised to the power minus at. Okay, then the final solution, the final solution, the final solution is obtained by summing up all of this, as we know. The final solution is obtained by summing these terms with their respective coefficients, with their respective coefficients. Okay. So I just want to give instances of some special cases of poles, right? Imagine if we have, so we've taken an example of a regular case, right? What if we switch over to this now, and then I have this here, okay, and then we talk about, say, we have repeated poles. So what we have up there is, yeah, those are just simple poles. So here, what if we have repeated poles? You know, those cases where you have the same answer twice or something. So for repeated poles, right? Imagine you have f of s equals 1 over s plus 1 squared, s plus 1 squared. Okay. So if you have that, right, that simply means that the function has a repeated pole at s equals minus 1 of order 2, because the power is 2, of order 2. Okay, so that's repeated twice, basically. So for a repeated pole now, we compute the residues using, so for a repeated pole, we compute the residues using the formula that the residue of f of s at s equals a is equal to the limit as s approaches a of dds of s minus a squared f of s, like this. So in this case now, substituting s, or substituting a equals minus 1, like we have here already. So if you substitute a equals minus 1, so it means that we have the residue of f of s equals minus 1 equals limit as s approaches minus 1 dds of s plus 1 squared times f of s. You know, the f of s itself is 1 over s1, 1 over s plus 1 squared, like this. So this simply cancels this out, as we know. So we have limit as s approaches minus 1 of dds 1. Okay, when you differentiate 1, it's just 0. So you have limit as s approaches minus 1 of 0. Okay, and that is simply 0. So what that simply tells us is that, so we say since this is a second order pole, okay, we need higher order term. We need higher order term. So that means that L inverse of 1 over s plus a raised to power n will be required, and that's usually t raised to power n minus 1 all over n minus 1 factorial e raised to power minus 80. So using this formula then, using this formula, okay, it means that L inverse of 1 over s plus 1 squared would simply be equal to, based on what we have, right, that will be t raised to power n is 2, okay, minus 1 all over 2 minus 1 factorial e raised to power minus a is 1 also, that, so that is equal to t all over 1 factorial e raised to power minus t. Simply, it is t e raised to power minus t. So that is L inverse of that, where we have repeated poles, s plus 1 squared. So that's the result in this situation. That's the final answer, and t must be greater than or equal to, t must be greater than 0. So that's for repeated poles. So the first one we did, like we said, is for simple poles. That first example is for simple poles. Where is it now? Yeah, so this is for simple poles. So where everything is just direct. So we have done repeated poles. Can we also do for complex poles now? So let me switch over to, okay, let's have this, and then, okay, we can go for this now. Okay, so imagine an example on complex poles. So here, you have f of s equals 1 over s squared plus 4. Okay, so we see that okay, if I say for this, right, for this, the denominator, s squared plus 4 equals 0 gives complex poles at, you have s squared plus 4 equals 0. That means s squared is equal to minus 4. That means s is equal to plus or minus 2i. So we have complex poles here. So we need to compute the residues. So to compute the residues, we rewrite f of s to be 1 over, it's twice, right? So we have s minus 2i into s plus 2i, which makes sense, right? So if that is the case, we now say that for complex conjugate poles, like we have up there, because this is a conjugate of this expression is a conjugate of this. So for complex conjugate poles, we use the standard inverse Laplace transform identity. So that means we have that the inverse Laplace of omega over s minus a squared plus omega squared is simply sine omega t e raised to power at. If that is the case, we can compare, right? So comparing with f of s now, which is 1 over s squared plus 4. Okay, we set a to be equal to 0 because a is 0, omega will be 4 then. We set a to be 0 and omega is 4. Because in this case, we just have s squared. So if we had like s minus 1 squared, that would have worked. So a would have been 1, right? So but here, a is 0, omega is 2, because here we have s minus a squared with s squared. So it means a is 0. Then we have omega squared and 4. That means omega is 2, basically. And so we can then have that L inverse of 1 all over s squared plus 4 is equal to, from this expression, sine omega t, that is sine 2t, okay, e raised to power sine 2t, sine 2t, this is e raised to power 0t for sure. L inverse. And then we have a division by 2 there. And I'm wondering where that is from. Okay. Let me be sure of that. Sine 2t. Okay. If adjusting the numerator, omega squared is 4. Yeah, so omega is 2. Okay. So L inverse of 1 over S squared. Okay. So the Laplace transform of sine 2t normally is actually 1 over S squared plus 4. 1 over S squared plus 4. Normally, if we have sine t, right, that's 1 over S squared plus 1. Now that we have 2, it's like this. So this will have to be divided by 2 to balance things out. So we have half sine 2t. E raised to power 0 is simply 1. So we just have this like that. So we divide by 2 because the standard Laplace transform of sine 2t has a numerator of 2, but our function had only 1. So we factor out half to match the standard form. So we have this now. All right, so that's that about the residue theorem for inverse Laplace. Okay, so let's take some practice questions. Let's take some practice questions and see how that goes. So practice. Compute Laplace, computes inverse Laplace transform of 1 f of s equals 2 over s plus 1 into s plus 4. Okay, then you have number 2, f of s equals s plus 2 all over s plus 1 into s plus 3. Number 3, you have f of s equals 1 over s plus 2. Number 4, you have, let's talk about repeated poles here. 1 over s plus 1 raised to power 3. Then number 5, s plus 3 over s plus 2. That's f of s now. Number 6 is like a lot, right? F of s equals s over s squared plus 16. Number 7, f of s equals 1 over s plus 2 squared plus 4. Number 8, f of s is 3s plus 5 all over s plus 2 into s squared plus 4. Number 9, Number 9, f of s equals 1 over s minus 1 into s squared plus 4s plus 5. So here you're going to have a combination of simple pole and complex poles. Number 10, finally. Number 10, f of s equals s plus 1 all over, that's s plus 1 all over s squared plus 1 into s plus 3. Complex pole and simple pole again. All right, so let me see your answers in the comment section, either on Facebook or on YouTube. Let me also know in the comment how helpful these videos are for you. And if you would like me to solve a problem or teach a particular topic, and of course, don't forget to subscribe to the channel if you haven't done that already. If you have, thanks a lot. And for everyone, don't forget to hit the notification bell so you can always get alerted each time I release a new video. And of course, there is a lot to interact with on the channel, going to 700 videos already. So don't forget to do that, to always follow up on them. And like and share so that more people can have access to the great content we have here. Till I come your way again, keep doing maths right. Bye.